All right, so another level of complexity that we have in grade 11 that we didn't do in grade 10 is looking at forces on another simple machine called inclined planes. So inclined planes are ramps, and we've covered that before in that they make things easier for us to lift things up. Okay, instead of lifting it straight up, I can push it slowly up a ramp, and I'll have to apply a little bit less force, all right? So the objectives of what we're gonna look at in ramps this year is learning how to label the forces, learning why it takes less force to push something up a ramp by analyzing the free body diagrams, and then learning how to calculate normal force and resultant force and acceleration. That's what's going to be in this video. Okay, so how do we label forces on inclined planes? Here's an inclined plane, a ramp, that has an angle of inclination of 30 degrees. That's how you say that. That's the 30-degree angle of inclination, okay? So 30 degrees is a common number because I like it. It makes it easier to do some trigonometry with. All right, so here's an object that has a weight of 100 newtons, the force of gravity, coming straight down. That's what that arrow represents. And that object on the ramp, if I let it go, is going to slowly slide down. So how are we going to calculate the acceleration? In order to do that, I need to be able to draw all the forces. So I know that there must be a force in that direction, which I'm going to call my resultant. There's a resultant force in that direction that causes acceleration in that direction, okay? But I can't quite see it. I only see one force, the force of gravity. How does the force of gravity acting downwards end up causing this object to accelerate in that direction? There must be other forces in play. Well, the other force is the normal force, okay, Fn. That's the force between the surface acting perpendicular, it's pushing at an angle. And because that angle is being created and that force is pushing down, when you combine them, they're not equally balanced. They're pushing in a net direction, and that net direction would be that. So how would I draw that? Well, if I drew one vector and I drew the other vector, the resultant would be the connection. So that's F resultant. That's my connection, all right? And that connection is my net force. So it's because the normal force is acting in that angle, the gravitational force is acting straight down. So what angle is that? Well, this angle here, because of similar triangles, is 30 degrees. Whatever the angle of inclination is, that will be the angle right over there in that triangle. And this happens to be a right triangle. Okay, so knowing that that's a right triangle, this is my adjacent side. All right, this is my opposite. Okay, and that is my hypotenuse. Okay, now with all that put together, you got to remember the rules of SOHCAHTOA so that we can figure out which trigonometry function are we going to use to solve these other sides. Okay, which trigonometry function am I going to use to solve my normal force? Which trigonometry function will I use to solve my resultant force? And for the force of gravity, I can calculate. It's even given to us as 100 newtons, okay? So how do we go about calculating the normal force? So quickly take a look at this triangle. How would you create a trigonometry function to calculate that side of that triangle, knowing that side? Okay, so pause the video, do it. Well, the way you would do that is you would say that this is the adjacent side, and that is the hypotenuse side. So adjacent hypotenuse would be cosine. So cosine theta is equal to adjacent over hypotenuse. Okay, now I'm going to substitute that in. So cosine of 30 degrees is equal to Fn, which is my adjacent side, divided by Fg. So then Fg cosine of 30 degrees is going to be equal to Fn. So essentially, Fn on any inclined plane, Fn is equal to cos theta mg. That's something you can write down. Cos theta mg is Fn, and theta is the angle of inclination. So cos of 30 degrees times 100 newtons. So Fg in this case is 100 newtons times cos of 30 degrees. I don't have my calculator on me, but that's how I would calculate the component of normal force, okay? So how do I calculate the resultant force? Well, the resultant force is here on that triangle. I have Fg, that's 100 newtons. This is my opposite side. So to calculate the resultant force, I use sine theta is equal to opposite over hypotenuse. We go back, show you that triangle again. Opposite is my resultant. Hypotenuse is the weight that I was given. Okay, so then mg, well, before I do that, sine of 30 degrees is equal to the opposite, which is the F resultant, over my hypotenuse, which is mg, okay, or 100 newtons. Okay, so mg sine of theta, which I have as 30 degrees, is equal to my F resultant. Okay, and in this case, it would have been 100 newtons times sine of 30 degrees is equal to the F resultant. Now I know that the sine of 30 degrees is 0.5, so then I would say 50 newtons is equal to F resultant. Okay, so my resultant force is 50 newtons. Okay, then with all that, how would I calculate the frictional force? So in addition to that, I would have a frictional force, and I would need a friction coefficient there. So how do I calculate the frictional force? Well, as we know, frictional force is equal to mu times Fn. Okay, so in this case on an inclined plane, it'll be mu times mg cos theta. Okay, why? Because I presented that here. The normal force is mg cos theta. Okay, so mu times mg cos theta will be my frictional force. So then, if I'm trying to calculate acceleration down a ramp, okay, then I would use Newton's second law, which says F net is equal to ma. And in this case, it would be Fr minus Ff. Okay, so Fr is acting down. Ff would be opposing it, is equal to ma. All right, so it would be mg sine theta, which is Fr, minus the frictional coefficient times mg cos theta is equal to ma. All right, that would be the complete derivation of that formula, okay? And then I would just have to, I'm not going to solve it, but I would say, I would give you the friction coefficient in here. That would be the friction coefficient. You know the mass, even though they gave you 100 newtons, the mass would be about 0.1 kilograms. So you have the mass, or you even have the weights, okay? And then 30 degrees is here, so you'd plug that in there. This would be 0.1 kilograms according to that. And then you'd be able to solve for the acceleration by moving the mass to that side of the equation. And would you take a look at that? If I move the mass to the other side of the equation, what happens? My masses cancel out. And I'm left with g sine theta minus mu g cos theta is equal to a. All right, so in class, I'm going to be giving you a variety of these problems that we're going to practice together. I don't want to put numbers in here. I want you guys to try to put numbers in here. But for a sample, you can go back to this and you can put in the numbers associated with this problem to see what the acceleration is. Okay, and I bet you the acceleration is going to be much less than 9.81 meters per second squared. You can assume, for example, that your friction coefficient is 0.3. Okay, try that out. If your friction coefficient is 0.3, you can plug that in here and you should be able to calculate the acceleration. And I'll guarantee you it's going to be less than 9.81.